Houston, contact with a test 1.
Hello, it's Scott Manley here. The New Horizon spacecraft continues its voyage into deep, deep space. In 2015, it of course flew by the dwarf planet of Pluto, and just at the start of last year, it made its last pass of an object for a long time. The small planetoid known as 2014 MU69, to some known as Ultima Thule, but now officially called Arakoth. This small remnant from the early formation of the solar system was too small and too distant from its neighbours to form into a full-sized planet. But now it's over 7 billion kilometres from Earth, and its trajectory isn't going to take it anywhere near any known object on its way out into infinity. But the team behind New Horizons recently decided to use their vantage point 7 billion kilometres from Earth to illustrate one of the fundamental principles of astronomy. The spacecraft took its cameras and pointed them at the nearest star, Proxima Centauri, a small red dwarf which is so faint that despite it being the closest star to the Sun, it is essentially invisible to the unaided human eye. And you know, this isn't scientifically a very interesting image. Indeed, I bet a lot of you out there can't even figure out which one is Proxima Centauri. Well, what about if I show you this picture that was taken at exactly the same time from Earth? So this is of course using that 7 billion kilometre difference in location to view the stars in the sky slightly differently, and seeing that Proxima Centauri appears in a subtly different location. And this is the first time that I've ever seen pairs of images that actually show stellar parallax in a way that we humans can easily pick it out and see the difference between the locations of the stars. And that might surprise many of you, because astronomers have been using stellar parallax to measure the distance to nearby stars for almost 200 years, and yet there haven't really been pairs of photos that show this effect. Normally, when astronomers are measuring stellar parallaxes, they're doing it from the vantage point of the Earth, and the Earth moves around the Sun, and if you carefully pick your observing times, you can get one observation that is 2 astronomical units distant from the other position, 6 months apart. So you expect stars in the sky to trace out these elliptical paths as the Earth moves around the Sun, and the larger the ellipse, the closer the object is. The size of these ellipses is, however, very small because the nearest stars are still quite a distance away. The largest parallaxes observed are less than 1 arc second. As you can see from this table of nearest stars, the parallaxes are listed in milliarc seconds. And for those of you that don't know, the 360 degrees that we use for a circle are too coarse for many professions. So each degree is split into 60 minutes, and each minute is split into 60 seconds. So there's 3,600 arc seconds in a degree. That is a very small angular measurement. So to compute the actual distance to the object based upon your parallax, you basically take the baseline that you're using, the separation between your 2 observing points, and divide it by the angular difference in radians. There are 2 pi radians in 360 degrees, and I know off the top of my head that there are 206,265 arc seconds in a radian. I know this because as an astronomer, the number is kind of burned into my head from seeing it all the time. Astronomers like to normalize their parallax values for a 1 AU baseline. So yeah, you just divide 206,265 AU by